Good day once again, students. Today we are going to talk about the relative masses. You see, we have been talking about atoms and molecules. We have also talked about atomic masses. We are going to talk about molecular mass. Now, these masses, you see, on what basis? What is the basis of their measurement? It is going to be very ridiculous for us to use the normal mass of the very tiny atoms in our everyday calculation. Then what do? We have a scale, a standard which we follow. We have a standard which we follow. And that standard, an isotope of a very important element, common element, an isotope of very important element is used as a standard on that scale. We have a scale we follow, and as a standard in that scale, an isotope of a very important element, carbon. Which isotope of carbon? We are aware that carbon has isotope 12, carbon 13, and carbon 14. The isotope we place, the isotope of carbon, we have as our standard in that scale of measurement, of measuring mass, is the carbon 12 atom. So we have a scale which has carbon 12 atom, and on this scale we place every other thing and measure and compare the mass with the mass of this atom of carbon 12. Carbon 12, an atom of carbon 12 on that scale has 12 atomic mass unit. 12 atomic mass unit. So if we place any other atom on that scale, we compare to the mass of one atom of carbon 12. One atom of carbon 12. So we say that is because now it is relative. When you say relative, you are comparing things. So we are comparing the mass of all atoms of all other elements with the mass of one atom of carbon 12. That is what we are doing. That is what we are doing. So that is the scale. If I have phosphorus, P, an atom of phosphorus, and I put it on this scale, where will it be? Below this or above this? Then a position will be there. It will have a position either above or below. I am comparing it with this. Since I'm comparing with this, the ratio of this to this, how much of this to this, then I will on a scale where this is 12, I'm now having this is relative to this, then it is not just the mass of phosphorus atom again, it is not just the mass of an atom of phosphorus, it is now the relative mass of the atom of phosphorus, because I'm comparing with carbon 12. So on a scale where the mass of an atom of carbon 12 is 12, where will the mass of, what will be the mass of phosphorus? On a scale where the mass of an atom of carbon 12 is 12, what will be the mass of sulfur? On a scale where the mass of the atom of carbon 12 is 12, what will be the mass of magnesium? On a scale where the mass of carbon 12 is 12, an atom of carbon 12 is 12, what will be the average mass of all these? We are talking about the average masses now. The average masses of all these, what will be their average masses? What will be their average masses? Put on that scale, what will be their mass? So that mass, we are not just going to call it their atomic mass, we call it their relative atomic mass. Relative to what? An atom of carbon 12. So we have relative masses, not just of atom, we have relative atomic mass. You can see on that scale we go relative molecular mass. What about molecules? What about molecules? I have molecules. CO2, carbon dioxide molecule. I can as well place carbon dioxide in that what? In that scale. Carbon dioxide molecule, I can put in that scale. What will be the mass of, the average mass of this molecule on a scale, on this same scale, where the what? Where the mass of an atom of carbon-12 is 12. H2O, same thing. H2O is a molecule of water. Okay, this molecule, same thing. I place it there. What will be the mass? What will be the mass of that molecule on that scale, where the mass of, on this scale, where the mass of carbon-12 is, atom of carbon-12 is 12. We also have relative formula mass. For relative molecular mass, let me come now one by one. Let me go one by one. So we're saying relative atomic mass of an element. Let's start from there. Relative atomic mass, you know why it is relative now, relative to carbon-12. Relative atomic mass of an element is the average mass of an atom of the element, is the average mass, average is very important, of an atom of the element on a scale. What scale? Where an atom of carbon-12 has atomic mass, 12 atomic mass unit. Where an atom of carbon-12 has 12 atomic mass unit. So that is our standard. An atom of carbon-12 has this as the mass. So on that scale, what is the, you say relative atomic mass is the average mass. Relative atomic mass of sodium is the average mass of what? An atom of sodium on a scale where an atom of carbon-12 has a mass of 12. So, relative atomic mass. This is defined as the average mass. Average, very important. This is defined as the average mass of an atom of an element on a scale where an atom of carbon-12 has a mass of 12 atomic mass unit. You may not write atomic mass unit, you just write 12, no problem. Okay, you understand what we are saying now? So on that scale, the average is very important, mass of an atom of that element on that scale. And what scale? The scale where an atom of carbon-12 measures what? 12 atomic mass unit. Same thing with a molecule, almost the same definition. The only thing you have to change is, for molecule, you can see, this is defined as the average mass of a molecule on a scale where an atom of carbon-12 has a mass of 12 atomic mass unit. Everything is the same as the atomic, relative atomic mass. The only difference is mass of an atom of an element, it changes to mass of a molecule. A molecule. We have defined a molecule before. Write that definition down. Write this down also. We have defined a molecule before. Remember, we defined a molecule. I hope you have not forgotten. We defined a molecule. We talked about a molecule. That a molecule is the smallest electrically neutral particle of an element or compound. Of an element or compound which can exist on its own. Which can exist on its own. So, a molecule now, we said, all this about molecule, you can go back to the video. Now, we are saying relative molecular mass. So, a molecule can be one atom, as in the group 0 elements. That is the noble gases. They exist on their own. So, and a molecule can be covalent compounds that can exist on their own. For example, CO2, carbon dioxide, can exist on its own. H2O can exist on its own. H2S SO2. All these covalent simple compounds can exist on their own. C2C6 H12O6. Glucose can exist on its own. They are molecules. They are molecules. We have seen different types of molecules. These molecules, if you have more than, if you have polyatomic, monoatomic, diatomic, apart from monoatomic molecules, I told you when I was teaching you molecules, that apart from monoatomic molecules, all other molecules contains atoms joined together by covalent bonding. So, if I am looking for relative molecular mass, which I call Mr, relative atomic mass, which I call Ma is here, relative molecular mass, which I call Mr, will be equals to, for carbon dioxide, it will be equals to Ma of carbon plus 2 multiplied by Ma of oxygen. This to be Ma of hydrogen multiplied by 2 plus Ma of oxygen. This will be Ma of hydrogen multiplied by 2 plus Ma of sulfur. This will be Ma of sulfur plus Ma of oxygen multiplied by 2. This will be Ma of carbon multiplied by 6 plus Ma of hydrogen multiplied by 12 plus Ma of oxygen multiplied by 6. This is what we are talking about. This is what we are talking about. So, if this is what we are saying, then to get the Mr from Ma is an easy job for us. To get the Mr from Ma, because when you go to your periodic table, you will see the relative atomic masses on the upper right left hand corner of every element in the periodic table. In the periodic table, you will go there. If I write chlorine, you see two numbers. You see here 35.5 and you see there 17. This is the Ma, relative atomic mass of chlorine. Now, how do you get relative molecular mass from this place? As I told you, go to your periodic table. Ma, say Mr for this. Mr will be equals to Ma of carbon is 12 plus Ma of oxygen is what? 16. 16 multiplied by 2. So this gives us 12 plus 32. Ma of carbon dioxide will be 44. So the summation of all the atomic masses of each atom of elements in that molecule is the Mr, or what you call relative molecular mass. Molecular, they have to be covalently joined together. This Mr equals to Mr of hydrogen is 1 multiplied by 2 because we have 2 of them, plus Mr of oxygen is 16. Then our answer is 18. For this, Mr of carbon, Mr of glucose, Mr of carbon is 12 multiplied by 6 plus Mr of hydrogen is 1 multiplied by 12 plus Mr of oxygen is 16 multiplied by 6. Everything, get the answer here, get the answer here, get the answer here, add everything together. That is the Mr of the molecule, glucose, relative molecular mass. Relative molecular mass. Now, the question now is, what if we are calculating and the compound we are talking about is not a molecule? It does not contain molecule as the individual units. It contains electrically charged ions. So it is an ionic compound. So it cannot be a molecule if it's an ionic compound. What if what we are talking about is an ionic compound, like NaCl? Like NaCl is ionic. Do we still say, when we calculate here, we say Na is 23 plus Cl is 35, then we will be getting 58. Do we call this Mr? No. We don't call it MR. We don't call it relative molecular mass, relative molecular, because it's not a molecule. This is not a molecule because it is not electrically neutral. It contains ions, sodium ion and chloride ion. The units are those ions. The units are not. There's no unit called sodium chloride. No, we just write it simply as this. We are supposed to write it like this. This is independent of this. The only thing is, because they are opposite charge, that's why they come together. They are independent. So the units are charged. So it's not a molecule, because for you to be a molecule, the units which can stay alone must be neutral, electrically neutral. So when we are considering ionic compound like this, what do we say? Instead of saying relative molecular mass, we say relative formula mass. For ionic compound, we say relative formula mass. For ionic compound, relative formula mass. The relative formula mass, we say relative formula mass for ionic compound instead. So we still do the same thing we had. Like we did this, we got 58 right now, we still had. So when you see relative formula mass instead of relative atomic mass, we know that we are almost talking about the same thing, but this time when we undergo the same process, but we are not talking about the same thing. So we undergo the same process. What is the process? Add the individual atomic masses in your calculation. But this time around, they will not call it relative molecular mass. They will call it relative formula mass. Relative formula mass. So we have seen this, we have seen this, and we have seen this. What about relative isotopic mass? You see, we already know about isotopes. You already know about isotopes. That isotopes of some elements, of course, all atoms of every element have the same number of what? A particular element, the atoms must have the same number of electrons, same number of protons. But the neutron may be different. And when this happens, so the mass of those two atoms with, or more than two atoms with different neutrons, will have different masses. We call these what? Isotopes. We call them isotopes of each other. They are isotopes. These isotopes, we want to get their masses. We don't call it atomic masses, we call it isotopic mass. Relative isotopic mass. From your IGC SCE, you know that hydrogen has isotope, hydrogen, deuterium, and tritium. Hydrogen 1, hydrogen 2, hydrogen 3. So if we are talking about the mass of an isotope, an atom, mass of an atom of the deuterium isotope, mass of an atom of this deuterium isotope on a scale where the mass of carbon 12 is 12, then you will be talking about what? You'll be talking about relative isotopic mass. Relative isotopic mass. I hope you understand this. So relative isotopic mass, this is defined as the mass of an isotope of an element on a scale again where the mass of an atom of carbon 12 is 12. Just put, you can see it, the yellow thing is the different, that's the difference. Here, the green thing makes the difference from the beginning. Here we have average there, here we have average here, and the other ones remain like that. So please don't make mistakes. Now we have seen these relative masses because we are comparing with mass of carbon 12. This is so. Now, how do we get these masses? How did the scientists get these masses? How? We have isotopes. Let's say I have chlorine isotope, or I have hydrogen isotope. I have hydrogen. I want to know the atomic mass of hydrogen. I want to know the atomic mass of hydrogen. Or I have a molecule, glucose. I want to know the molecular mass of glucose. How do I know this? And so many other things. But for now, let's talk about the masses, the atomic or the molecular mass. We use a process known as spectrometry. Spectrometry. In the laboratory, we use mass spectrometry. Mass spectrometry. Don't be scared by this. Nobody will ask you to draw it, but they can ask you to label it. So mass spectrometry. By the time you continue to label it, after some time you will understand it. Mass spectrometry is what we use to do what? To find the mass of what? Of molecules, of isotopes, of molecules and atoms. Isotopic mass, formula mass, atomic mass, relative formula mass, relative isotopic mass, relative molecular mass. All these relative masses, we use mass spectroscopy to find their mass in the laboratory, in heavy laboratories. Now, how do we use this? And first, before you know how to use it, you have to know the components. This is called the vaporizer. V. Vaporization takes place there. Here, ionization takes place here, and it is called bombardment chamber. Bombardment. So that means before ionization takes place, you know the meaning of ionization. Ionization means you add electron or you kick out electron. What do you do this time around? We kick out electron. So that means it's just like you want to pluck. In those days, if you want to pluck mango from a tree and we cannot climb the tree, we take stone and we start stoning. We start targeting the mangoes. Same thing, when the stone gets to the mango falls off. Same thing, this is called, we have bombarded the stone on the mango. So we bombard certain things on whatever we have here, bombardment chamber here, so that ionization will take place. So just as the mango falls off from the tree, electron will fall off from whatever is coming from here because of bombardment here. That's why we call it ionization, because when you say ionization, you are talking about either you add electron or you remove electron from an atom or molecule or a substance. Then we get to accelerator. Accelerator. This place is the accelerating area. Acceleration means you make a movement faster. You increase the speed. Accelerator. You increase the speed. You know this from your IGCSE physics. Something that makes you accelerate. That in your father's car, when he presses one thing on the right side, the car moves faster. It accelerates. It speeds up. So, accelerator. So, it is here. Then after that, we get to a point here where the thing is curved here. At this point, we have magnetic field here, and we see our magnetic field, what it causes. And we say this is the deflection area. This is the deflection area. This is the magnetic field, and deflection takes place. This is magnetic field, and deflection takes. So deflection takes place here. Deflection takes place there, and that's the magnetic field, which causes the deflection to take place there. And this side, the detector, you can see vaporization, ionization, acceleration, deflection, detection. Detection. What are we talking about here? Whatever is coming from here is detected from here. Is detected from here. In some textbook, it is drawn more complicated than this. This is just a very simple drawing. So this may be given two areas. So they say detector and recording. So maybe like a computer record. You see it on the computer. So computerized. So we are going to talk about this now. So what happens here? Now, I have again, V is vaporization. I, ionization. A, acceleration. D, deflection. And the last, the detection. Detection. So let us now see how this works. Let us now see how this works. In some syllabus you have this, how this work, and in some syllabus you don't. If you don't have it in your syllabus, do not bother yourself about it. But if you have it in your syllabus, continue with me. How does it work? We put the element or molecule in this vaporization chamber. It is changed to vapor. And when it changes to vapor, of course, naturally it will move. It moves out. When something changes to vapor, if it is a solid and it changes to vapor, that means it has, if it is an atom, if the unit is atom, it changes to one atom. If the electrically neutral unit is atom, like the noble gases, so it's atoms. If it is the electrically neutral particle is molecule, like glucose molecule, you put some glucose there, you vaporize it, it turns to C2H5 and C2H12O6, C2H12O6, C2, millions of them. If it is water, it changes to H2O, 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 or individual molecule. Let's talk about atom first. So you have here atoms. You have your atoms here. It vaporizes, it comes out here. It comes out here. It gets to this bombardment chamber. This is heating. This is heater. This one is heater. When you heat, and it is cathode. Cathode, we call it cathode. Cathode, from cathode, what comes out from cathode? For those of you who did Cambridge, cathode, remember? Thermionic emission. Thermionic emission, you remember? So when you hit this cathode, electrons will come out. Fast moving electron will be bombarded. When the electron, don't forget, coming from here, your vapor now, which contains whatever you are talking about, when it gets to that place, each of these atoms, which is now gaseous atom, will be collided with by what? The electrons coming from the what? Cathode. Fast moving electron from the cathode, we collide with this what? We collide with these atoms you have there, and it will knock off what? It will knock off electrons from them. It will knock off electrons from them. When it knocks off electrons from them, what do you see? When it knocks off electrons from them, what do you see? You see, when electron is knocked off from them, what do you see? You see, it becomes positively charged ions. When electron, for example, electron is knocked off from chlorine, Cl. Electron is knocked off from chlorine atom, it becomes Cl+. It becomes Cl+. Electron is knocked off from hydrogen, it becomes H+. Electron is knocked off from sodium, it becomes Na+, like that. So when you knock off electrons from them, they become positively what? Charged. These positively charged ions now, which is what we are interested in, the positive charge that is positively charged. This ionization accelerator, it is electric field. Remember, for those of you who did Cambridge before, you remember when we're talking about thermionic emission, cathode ray oscilloscope. Unfortunately, I'm not sure you are supposed to know this at grade 12. So now this place is giving a negative electric field. When you give this place negative electric field and positive is here, it will attract the positive. It will drag it. When it drags it, it passes through this hole. When it passes through this hole, it moves, because that force has given a what? Has given an acceleration. So because this one is switched on, the accelerator, because it has a negative electric field which is negative, then it drags the whatever positive ion that is coming from here. Don't forget, neutral atoms coming from here, then electrons coming from here, from this cathode, bombarded, and does what? It knocks off electron from them at this point. Okay, when the electron is knocked off at acceleration, what happens? It is electric field, negative electric field is here, which causes the attraction of this positive ion here. So, and its attraction means force of attraction, a force, bam, a sudden force. Something changes to ion, positive ion, and a sudden force pulls it. When it pulls it, what happens? It accelerates because it's a resultant force. And you remember in your physics, to every resultant force, there must be an acceleration. So that acceleration causes it to fly by this way. As it flies by, it enters a magnetic field. This is a magnetic field. Magnetic field. This is a magnetic field in this area. That's why we made this to curve here naturally. Design it to curve because we know whatever is coming this way, we curve. Because whenever a charged particle enters a magnetic field, it changes direction. We know that. It tries to curve. It tries to move in a circular manner, so it changes direction. From the straight path, it changes direction. It enters the magnetic field and it changes direction. So this is the magnetic field. Why did it change direction? And why must it go down this way? Why not up? Why does it have to go down? Remember from IGCSE, your Fleming's left-hand rule. That nobody will ask you here, but you remember that that will show you the direction of this positive charge. For those of you who remember, but nobody will ask you this time. So, it enters the magnetic field. Why did it turn to 3? Why did it divide into 3? One thing was coming and it divided into 3. A big surprise. It will not, if it enters the magnetic field, it will not only change path from the straight path, the way it changes path depends on the mass. The way it curves depends on the mass. The way it deviates depends on the mass. A heavier atom will deviate less. So, heavier atom. This is having higher mass, heavier. We deviate less. And the least heaviest, least heavy, we deviate less. Look at it. Sorry, this one will deviate less. It will not curve too much. The heavier one will deviate less. It will not deviate too much. But the least heavy will deviate more. The least heavy will deviate more. Will change direction more. And of course, this one is in between the two. What does the deviation? I told you, when it enters the magnetic field, it deviates. And the deviation depends on the mass. So that shows you that if the thing is coming this way, for it to deviate and turn to 3 things like this, it means it has 3 isotopes, because each of the isotopes have different masses. So the deviation will be different. Again, one thing coming like this, everything coming, got to this place where deviation will occur, and it deviated into 3. Wow! How did this happen? I will say the deviation depends on the mass. If the mass is very big, deviation will be less. So, if the mass is very small, it will deviate so much. So that means all the things coming from here, the atoms coming from here, contain 3 isotopes. 3 different masses coming together. You will not see it until you get to a place where mass affects the deviation. When it gets to the magnetic field, the mass affects the deviation. In the magnetic field, the one that is deviated the most is the lightest. Least heavy, that is lightest. Lightest. The lightest in mass deviates more, cause more. Deviates the most. For you to see 3 here, that means whatever you have here has 3 isotopes. But this isotope is the heaviest. Because there are 3. And the lightest is this isotope. So it divided into 3 because the magnetic field, in the magnetic field it must deviate, and the deviation depends on what? On both the strength of the magnetic field and the mass of the thing that is deviating. Both on the strength of the magnetic field, the deviation depends on both the strength of the magnetic field and the mass. So since we have 3 different masses coming, when it comes to this place, they separate. The one that is heaviest deviates the least. The one that is followed by this one, and the one that deviates most is the lightest one. I hope you understand this. Then, we have seen why it divided into 3 now. Because the magnetic field makes it deviate, and the deviation depends on the magnetic strength of the magnetic field and the mass. The strength of the magnetic field right now, we keep it constant. But since it divided into 3, that means whatever is coming here has 3 different masses. So that means we have 3 different deviations. Then what do we see? We get to the detector. At the detector, we detected only one thing. One thing is recorded. Only one of them is recorded. We don't want one to be recorded. Then what do? This magnetic field, we have the ability to change it. We change the magnetic field gradually. If we either increase or decrease, we get at a point, we get this one into this. Why these 2 will not be there again? We get this one there, the heaviest there, because we have changed the magnetic field. And at another point, again, that's when we change the magnetic field, keep that, when this one gets there, it gets recorded also. So 2 have been recorded. When this one is recorded, these 2 are not recorded. Then this one gets recorded. And sometimes it may be curved enough to get here. It doesn't matter. This may be curved enough to get here. That means 3 recorded at the same time at that magnetic field. If that is not done, and we are sure there are 3 there, so we adjust and this gets there. We adjust the magnetic field for this to get to this place, for it to deviate up to this place. We adjust the magnetic field again for this one to get to that point. So for us to get every isotope detected, we have to adjust the magnetic field because their masses are constant, so the deviation is not going to change until we adjust the magnetic field. Because the deviation depends on the mass and the magnetic field. First, we get it, we get the ones we can get. If we can get the 3 of them, they are a particular magnetic field, good. But they will appear at 3 different places. If we cannot, we adjust the magnetic field and they get there. We get them there by adjusting the magnetic field. I hope you understand this. Then, this can be a photographic plate which you will develop to see this result, or you can connect it to a computer. The computer will process it and show you on the screen. This now, which will be shown to you on the screen, will come out like this. This is called the mass spectrum, the result on the film, on the photographic plate, or on your computer. This is called the mass spectrum, mass spectrometer. This is mass spectrometer. Mass spectrometer. The whole thing is mass spectrometry. This is mass spectrometer. This instrument. But the whole process is mass spectrometry. And the result that comes out from here is the mass spectrum. Then, in my next class, we are going to work on the mass spectrum. What about the mass spectrum? How do we process the mass spectrum? How do we get the mass from the mass spectrum? The relative atomic mass from the mass spectrum, how do we get it? If it's molecule, the relative molecular mass from the mass spectrum. How do we get this? This is going to be in my next class. So students, you have seen how the mass spectrometer works. So we're going to talk about what it has detected in my next class. If you have any question, do not hesitate. You know the normal thing. Send your email to Teacher Hafiz and it will send back to you a video to answer your question. Custom made for you. We always care for our students. Good day and God bless.